So what we saw in the video with Bruce Yaney and all his demonstrations were a lot of examples of what we call induction charging, or charging by induction. When we're talking about induction charging, what we're really doing is bringing a charged material close to an object and causing the electrons within that material to separate and polarize. So we're creating a charge separation, and that's just a movement of the electrons. That charge separation is sometimes known as a polarization. As you saw in some of the graphics, you see those electrons go to one side of the material. Remember, the protons don't move because the atoms aren't physically moving, but the electrons can kind of flow around because they're in this electron cloud. All right, so we're creating a charge separation in a material. By bringing a charged object near that material. And that charged object could be positive or negative. Either way, it's going to have an effect on the electrons that are in the material. So when we look at that wall, when we were playing with the balloon on the wall, those electrons are evenly distributed amongst that wall. But the moment you bring a charged object close to it, if it's a negative charge, it's going to push those electrons away while not actually moving the physical atoms. So the protons stay where they are, which means the surface becomes slightly positively charged. If you were going to bring a positive charge close, the electrons would huddle close to the surface, making it negative because they would be attracted to it. So this process is what we call inducing a charge. And again, we don't have to touch it. So one of the biggest things that we reference here is that it's without touching it. So there's no physical contact and therefore no transfer of actual electrons, right? And as a result, it's actually a temporary charge separation. Or a temporary charge or polarization. Since the moment we move that charged material away, the electrons will return to their original position. They don't like to be near each other either, so if there's no other charged thing around it, they'll just float right back to where they want to be, to where they're neutral. So they'll return to their original positions when the charged object is moved away. So again, this is what we call induction. Now, again, the biggest thing about induction is it's without actually touching, which means there must be some kind of charging that occurs with contact. And this is a type of charging we call conduction charging, or charging by conduction. It also happens to be that to charge something by conduction, usually that thing you're charging is going to be a conductor itself, so that the electrons can actually flow into it. If you're touching an insulator, that insulator doesn't allow electrons to flow freely, and therefore you really wouldn't create a very good charge, right? But if you touch a charged object like that charged balloon to something metal, that metal object will actually takes some of those electrons from the balloon. So charging by conduction is a transfer of electrons. This time by contact between a charged object and a neutral conductor. So as we'll see a bunch of demos in the next video, he'll get into this a little bit, and you'll start to see how we charge by conduction. But I want to introduce this concept before we actually watch this video. The other thing I want to get into is really how we actually can remove charge. Right, so that's the thing I want to talk about a little bit right here. So how do you remove charge? And there was something interesting when you looked at that balloon and the sweater when you're playing with that PhET simulation. Once you rub the electrons onto the balloon, if you notice, you couldn't really put them back onto the sweater. They really didn't want to go back onto the sweater. And the reason is the sweater is an insulator, just as the balloon's an insulator, right? So those electrons don't really want to flow between them, even though those materials, one's now positive, one's negative. There's just not a lot of movement there. And when you rub those materials based on where they are on that triboelectric series, they tend to want to give up or take electrons. So how would you get that balloon to lose charge? Well, you need to give those electrons somewhere to go that is willing to take it, right? So a charged object needs a source to take its extra electrons or to give it electrons if it's positive. Sorry, a charged object needs a source of either an object that is missing electrons or an object that has extras, right? So a source that can take its extra electrons. That would be for a negative charged object, or give it electrons if it's positively charged. And by doing so, that object would no longer have a charge at all, right? And so you could therefore remove its charge. Now, this also kind of explains why you have that attraction between opposite charges, because they want to remove the charge from each other, right? So this concept of removing charge actually causes that attraction. Now, what you can also get is a scenario where the source that is taking those extra electrons or giving electrons is not actually charged itself, but it has so many atoms and electrons available that it can give up a few to a charged object to help discharge it. Right? So if the source is big enough, right, it can both give or accept electrons. And in doing so, it would take the charge away from electrons, and it would take the charge away from that object, right? And if you think about it, there's one object that's really big that has almost an infinite number of atoms and electrons, and that large object would be the Earth, right? And so the Earth, also known as ground, right? So the ground is an infinite reservoir of atoms. So if I have an object that is missing electrons, well, it could get them very easily from the ground. And the ground can pull electrons from anywhere in the entire Earth, right? And if it's got extras, those electrons can go there as well, right? So we call this process grounding an object. Grounding is the act of discharging an object by transferring electrons to the ground. And we see this a lot in our day-to-day life. If any of you guys pull the plug out of the wall, a typical plug will have, and we'll get into electric circuits, but usually you have a couple different prongs here. You have two prongs that go into it, and then you got this third prong that goes into that. And forgive my drawing here; it's not a very good plug. All right, but those are the two plugs, and you get that third prong, and you got this wire going through, and you actually have one wire in here, another one going to this metal connector, and you have a third one going to this prong. And this is called our ground wire. And if you were to go to your circuit breaker box, you would see there's a wire that's literally exiting your circuit box and going into a spike that's driven into the ground. If you look at a telephone pole, if you're in the city, you walk by a telephone pole, you'll see at the bottom there's usually a metal wire that's connected to a spike that goes right into the ground, right? So you have a ground wire. If anybody's ever worked with electrical circuits, people who are soldering or working with those will have a little wristband on with a little metal contact to their skin. And if your body builds up static charge by rubbing your feet on the carpet, like John Travoltage, right? And you're going to discharge. Well, rather than discharging into your circuit board and frying it, that charge will constantly be going through that contact from a wire, and you usually touch it to a big metal desk or some kind of metal contact, and you can ground yourself. So it keeps yourself from zapping anything with the static charge. So you got a lot of examples where you see grounding occur. But if I want to remove charge, really all I need to do is touch something metal, and as long as that metal is touching the ground somewhere, that charge will be dissipated. So we'll talk about grounding, but you'll see this in the videos as well. The one last thing I want to talk about before I show you another video here with our man Bruce Yaney is this thing called a Van de Graaff generator. I want to explain it a little bit so when you see it, you kind of know what you're seeing. So a Van de Graaff generator is a device uh, that basically creates a buildup of charge on a big metal dome, and you can do some pretty cool things. Kind of creates little mini lightning bolts. It can kind of zap you. They look pretty cool. But basically, what I want you to understand about a Van de Graaff generator, it's kind of like a electric vacuum. All right, so usually you have some kind of metal dome, all right, made out of metal, and there's some insulating tube, and then there's like a a box here and, a cord to go into the wall, and you have a switch. But inside here you have a wheel here and a wheel here and like a rubber belt that basically just runs up and down here. And this metal dome will have a little comb that's kind of touching and making contact, right? So conduction. And as this thing rotates, it's basically pulling out electrons from anywhere around that surface. So any electrons that are building up, right? So you have all this positive charge. These are all the physical metal atoms, nucleus, right? And those electrons that are associated with them end up getting transferred down and then out to ground, right? So you're basically continually pulling electrons out of that dome. And if I bring an object near it, right? If I have an object like my hand, and I'll try to draw a hand here, not the best hand, right? That has positive and negative, right? So here's all the positives on there, right? But it also has some negatives. Well, those negatives are going to want to go into the Van der Graaff generator. I'm going to get a little shock, right? So it's going to suck the electrons right out of my body. And even the atmosphere around you here, it's kind of snap and crackle. So I want to kind of show you. So again, think of the Van der Graaff generator as a device that acts like an electron vacuum. That takes electrons from the surroundings and brings them to ground. And we would say it grounds them. All right, so it gives them a pathway to the ground, literally through the wire out that's plugged into the wall. And in doing so, it maintains, it constantly builds up a charge on the dome. And that dome is metal, so it's a conductor, so those electrons flow really freely through there and are removed very easily. So the metal dome builds up a positive charge. Now, I've actually taught it both ways, where you could say it's actually loading electrons into that dome. Uh, you know, if he's watching a video with Bruce Yaney, he talked about it with a positive charge. I think that's most people would say it that way. I think it also depends on what materials these wheels are, and that triboelectric series. So I think you can actually build these to build a negative charge in the dome. And so I've kind of taught it both ways, but we'll consider the dome to be positive when you look at these demonstrations. So if you understand what this generator does, and he has a homemade one with like a Coca-Cola can. He does a homemade version, but that's basically all it is. And as he's holding it, those electrons are passing down from the Coke can through a little belt and then out and actually into his hand, and his feet are touching the ground, and so those electrons flow through him to the ground. And so that's basically how his little Van der Graaff generator works that he built up. He might even have a little wire running from it that you can't see behind the desk. So I want to run through all that. We're going to revisit another video here, and we're going to see some demonstrations where he discusses induction a little bit more, and then conduction and the difference between it. Actually does a really good demonstration with two cans, some tuna cans that he put together that demonstrate really the difference between conduction and induction. So we'll break right here.